Hi everyone, my name is Savina Papaioannou. I'm a chemical engineer with a background in materials science, and in this video I would like to shortly introduce you to my PhD topic, which is part of the European funded project Heat4Energy. Heat4Energy project aims to develop a technology to convert low-grade waste heat into electricity. Low-grade waste heat indicates the waste heat released by industrial and chemical processes and which peaks just above room temperature. So how can we efficiently convert waste heat into electricity? The developed technology will be based on Faraday's law of induction and thermomagnetic materials. Heating or cooling a thermomagnetic material results in a significant change in its magnetization, and when a conductor is exposed to a changing magnetic field, an electric current is induced in the conductor. Here you can see a thermomagnetic generator setup. In this setup, water-flowable thermomagnetic elements are incorporated in the demonstrator to be used as heat exchanger components. My contribution to the project is to identify the structural defects leading to failure of thermomagnetic materials and parts, and to select materials and parts that withstand the conditions in the demonstrator for 1 billion cycles. To achieve this, the non-destructive characterization technique of X-ray computed tomography is used. A typical XCT scanner consists of an X-ray source, a sample manipulator system, and a detector to capture the 2D projections. This characterization technique will serve as a key tool for evaluating the morphology of the developed components and identifying trends that enhance material performance. After obtaining the reconstructed 3D image, a scientific image processing platform is utilized for image analysis. It enables the user to begin with a raw image, then segment it into different phases, separate and label each object, and finally perform quantitative analysis. The data analysis includes critical information about the sample surface area, density, void fraction, mean 2D area, and its distribution along the printing direction. In addition, we can assess signs of failure and the formation of secondary phases. These parameters have an impact on material performance in terms of its heat transfer efficiency, magnetic and mechanical properties. In parallel, the additive manufacturing process of 3D dispensing will be used to develop structures which will be tested in the demonstrator. The main target is to optimize the process parameters and obtain porous structures with good hydraulic properties, large surface to volume ratio, and good long-term stability. I am based in Berlin and conduct my research at BAM in the Department of Materials Chemistry. During my research, I will be given the opportunity to travel and collaborate with our academic and industrial partners. During my first secondment at TU Delft, we will develop a thermomagnetic powder for 3D printing. At Magneto BV, we will work on the 3D printing of thermomagnetic blocks, and during my final secondment at the University of Ljubljana, we will test the most promising thermomagnetic parts in the demonstrator.